Okay, good afternoon. I think you guys had a good lunch. Okay, good. So we'll continue with the session. I think thanks to the great speakers in the first half, with exciting topic, more interest in the industry, and this is where a lot of growth potential is there from a lot of the OEMs as well as from a lot of the semiconductor companies. Both are venturing into this market, and that is where this is becoming more and more critical. So we'll just get into area. We will discuss why ISO26262. I think a lot of people discussed about it, and what is the thing which for every design, why how I take care of DV. I ensure the quality or the safety critical things needed for my SoC or for my subsystems. And first we'll see the how, we'll see the why and what of it, and then we will also talk about how it is being done using the Cadence flow of things. So we'll go through it. The flow will be more or less the same. We will go with our approach. We have certain ways of doing things, and we think that is one of the better way in the industry which we're doing. But be it any vendor or anything, I expect the things should be more or less in the similar methodology. So okay. So okay. So overall, I think a lot of people touched upon the safety requirements and overall flow. We'll talk about FMEDA creation and the safety analysis of the FMEDA, and we will primarily focus on the digital side of the verification, being like more big D designs kind of thing. But also we'll touch upon something on the analog and mixed signal flow. I am not an expert on the AMS flow, but I'll briefly touch upon like how we do things and how it is impacting for the overall flow, and also a little bit on the Cadence way of using the platform for even to the implementation stages, how we do it kind of thing. And overall, in the end, like some summary and some success stories where Cadence we had partnered with a lot of these OEMs and the semiconductor companies, and we had some success stories. I'll just brief about it. So why, as I mentioned, this is the growing market, and key trends are moving towards automotive. There was a mobile zoom market boom in the early 2K stream, but now most of the trend is moving towards automotive, and we can see due to this, a lot of these new technology needs are also being developed to cater to this automotive market, especially the 3D IC designs, the chiplets, and also on the lower nodes kind of thing. Why these things are needed? Because it is not like now the automotive is more on like from a structural or way of connecting things and doing things. Now most of the control is getting into a central control network, which needs like more number of chips and more number of interconnected networks into this. So that is where more and more control is getting into the IC design kind of thing. So you need more ICs and you need more high-speed connections inside the car itself and the way of controlling things inside the any automotive kind of thing, right? So as I said, industry is responding to the supply chain disruption. So we see a lot of these OEMs and tier ones are getting into the soft designs than the traditional semiconductors. We know the Teslas or the other biggies, the top mobile companies are also getting into the automotive segments kind of thing. And the traditional semiconductor companies were already there in the other mobile big markets. They are also entering into the automotive space. Examples, there are the Qualcomm, the Samsungs in the world. They are getting into more and more of the software the automotive platforms kind of thing. And in addition to this, we are also seeing there is a huge startup ecosystem which is getting built up, not just in US or in Europe. You're also seeing this trend happening in India with Ola and others coming into the bigger play and getting into this kind of thing. So there is on the various segments, there is a lot of growth in each of the segments, but you can see like as overall there is a good potential growth in the overall automotive industry. That is the primary reason where we are talking now. There is depth of demand in this, and there is more than the demand, there is a lot of focus on the safety things in this. Some examples, the top OEMs in the world, Ford and Jeep Cherokee. As you can see previously, a lot of these control networks were using, if you've seen the previous cars kind of thing, there is like a lot of all these networking things were usually the copper cables, like a lot of these copper cables running in the car and a lot of these instrumentation clusters getting connected now. Now, we still have the mechanical controls at the top level to just connect to the physical end connections, but however, all these are centrally controlled by what we call as like a vehicle computer or a integrated compute network, which has a lot of connections to a lot of various sensors, and it also connects to a lot of these actuators, which takes care of the end results of this thing. So this is at a very high level. There is a multi-threaded OS which is running in a real-time car with a lot of these hypervisor kind of things there. And each one has a different functions where we need to have a real-time response as quick as possible. That is where the safety, it is much more safety critical. This is the famous V diagram. I think not any one of the presentations will be complete without this. So where this is the overall ISO26262 standards, where we are, as a semiconductor companies, we primarily focus on 9 and 10, and there is a new chapter 11 which is also added to give details about the semiconductor process analysis. Some of this is the ASIL standards. We have all these three metrics, what we call the SPF from the LFM and the PMHF, which all three are interrelated with different metric data, but all these interrelated data will have a combined metric value which needs to adhere to follow to a particular ASIL standard. Most of the automotive components in general, any of the chips in the market are tendency, we can say, like will follow the ASIL A, which is predominantly I don't need any safety. But the components which are primarily, I think Mike's slides also had a slide with a car and the rear light being like a ASIL B or a ASIL A kind of standard, whereas like a lot of these brake lights, the headlights, they will be prominently into the ASIL B category, whereas your cruise control or adaptive controls will be kind of like, yeah, that is in the ASIL C category, where there is an autonomous control where you can still take control. But whereas some of the top components like your EPS, your ABS, your airbags, which is like your power steering or the anti-braking systems or your airbag actuators, all these are coming to the ASIL D category, right? So automatically when we take these into considerations, that means all the controllers which are behind this, now as the computer is going to control these operations or the enablement of these things, we need to follow these measures very strictly to avoid any hazardous fatal things. Getting into the FMEDA, the slide was supposed to build one by one, but it came as a whole. So where we will go into detail from architectural till the overall DV kind of view. But we start usually, whenever we start with the functional safety concept, we start with the functional concept. I think in my slides also they brought it up, like we put like about the HARA stuff, we talk about it. If there is a slippery road and a wet road and the brake control is failing kind of thing, what happens? That is a functional concept kind of thing. From there we derive the architectural level data. Once we don't have a design, so we start with an architectural estimation. That is where the FMEDA architectural exploration starts here. So here you start with, you don't have a design, but you know what are all the blocks there, you know what ASIL library you're getting into, you take a estimated data and you create a FMEDA at the architecture level. So these two you are doing at a estimation level, right? You don't have your design implemented or you're running anything on this. So once you do this you'll have it at the estimation level. You just do an analysis at estimation level. This can be a little bit more optimistic, but once you get into the details, once you implement that, once you have your net list or the number of instances, you have those details, then you can have a detailed FMEDA. You just populate that data into the FMEDA. That will give you a little bit detailed FMEDA stuff. So once you have this detailed FMEDA, now you are going to start your verification process. This is where any of the DV engineers' role will be more needed. So here we will start with, I'll come into the next slide where usually we do we'll do the good simulation, and then we inject a false simulation, then we collect the data, and once we have all the fault metrics, we do a back annotation with respect to the FMEDA, and we collect the overall safety metrics. So for this slide will give you the overall picture, what the cycle of things which are happening, and the next slides we are going to talk about how we are going to do this using a cadence flow of things. Okay. So as I said, that's the cycle. We start with a architectural FMEDA, and we use this flow to get into a detailed FMEDA and get the results and implement it back to the overall FMEDA. So we are also working with Accelera. We have a safety format which is called the Unified Safety Format. Accelera is a standard which is like can be called as an incubation to the IEEE standard. But currently IEEE also there is a working group which is working on safety standard. So most of the things we are adhering, but in final whatever IEEE standard is going to be there, Cadence will follow that standard also. Okay. So we call our safety platform as Midas safety platform. So we start with the FMEDA and we create the safety verification plan based on the FMEDA inputs. Once we have this, now we get into the design level details. That is where we run the actual design. Using the USO format, we can gather all the information. We can either use it into our verification flow, where we can do the complete safety verification. On the same USO format, because we have all the gate level details, we can use it to the safety implementation flow, where we can take that details into our synthesis tool, Genus, and the Innovus, and we can implement it also. Now, this Midas seamlessly integrates with the safety flow, where you can have your Xcelium, which is your logical simulator, which runs both your good and your safety simulation. It does also connect directly with the formal engine, which is Jasper, where we use for the fault testability or the fault collapsing mechanism. And if you are going to run a larger SOC level cases or your software libraries or the STLs, you can directly, from Midas, you can directly launch it into the Palladium, and you can launch the fault emulation campaign. So this is one window for a user. It is going to be just one window for a safety, I'll say safety engineer. I'm not going to say a safety verification engineer. For a safety engineer, once he gets all these data in some format, like USO format into the Midas platform, the same, he's going to use that GUI, he's going to use the flow, and he's going to either take it to the verification campaign and run this using the safety campaign, or you can take it into the implementation campaign and you can use this window for the safety implementation. Also, as I said, we use our Spectre engine, similar to the Xcelium, which is the digital simulator. Spectre is our the industry standard or industry leading AMS simulators. So where we can also use for some big D, small A, big A, small D kind of designs where you want to launch of the analog campaigns. And since it is a single integrated window, you can get all these metrics in one place, and you can get the final safety metrics. That is the biggest advantage of this unified flow, which is Midas. And some of the configurations, I'll come into the next slide, what you are using for the FMEDA or your safety metrics can be directly stored into a particular database, which is called the Midas database. So all your config things are there. So you are working on a particular SOC or a subsystem now, and you are getting into some derivatives. You can use this database to enhance the next thing. Assume currently you have in one of the safety campaigns you are using ASIL-B, or for the next generation you want to do ASIL-C or ASIL-D. You can directly take this database, tune your configurations or your safety things directly in this tool, and you can take it to the next level. We'll get into more details in the next slide, but this is the overall picture. What is coming? Get into the next.
You have a big talk. So we need to go through with the fault accessibility as well as fault simulation, or can we go directly to Palladium itself?
Depends. If you are going to just do the entire SOC STL directly, you can't. You can do STL simulation in logic simulator also, but you know how much time it is going to take. If you are taking a simple example, if you are taking a Cortex M52 and there is a STL for that. If you are going to run in simulator, it is going to take like 8 to 12 hours of the simulation. Okay. Whereas if you run in Palladium, it is going to be just like 3 to 4 minutes. So this is the time difference. If you want to run like, and even in the fault, if you know the list of number of faults for which you need to run the thing, right? If you are going to run a campaign in simulation for at the STL level, this is going to be very, very performance overhead will be there. So this is going to take days, whereas this will take in the minutes kind of thing. So that is the unit.
Can you relay on the Palladium?
Yes, we can. We are already doing at one of the top 2 semiconductor companies. So we had already used the safety flow, and very soon you will see some certification. We have some success stories which will come into later. Okay, so this is the MIDAS platform, as I said, which can drive both analog and the digital flows based on the. Let me just get my. Which is driving both the digital and the analog safety flows. We can do architectural exploration. That means I can start with the architectural FMED analysis. We'll come into the next slide. We'll see that. Also, we can do early safety analysis or a detailed safety analysis, which is nothing but a detailed FMED. We can do both the things directly in the same GUI. And as I said, our currently we have this support for USF. But again, we also support whatever IEEE is going to get into things. And this is how the GUI looks, where it will give you all the details and other things. This seamlessly integrates with the very same safety campaign manager, which we'll see in the next slide. So this is the early architecture FMEDA setup. You just build the slides. So right. So you can at the architecture level, you just go to the GUI. You just select what type of project you are entering, what type of ASIL you need, and whether it is a architectural or a detailed FMEDA which you are getting into, what type of report you need, what is the entity, and then based on this, you then come into the next 3 steps where you are creating an FMEDA. You either select your in the entire SOC, you can select parts. From the parts, you can select subparts. Assume your part is your CPU. From a CPU, you can have a subpart based on like a MAC or any other adder, subtractor, whatever it is. And for each of this, you can have a failure mode creation directly in the GUI boxes. And you can have your safety mechanisms. You can map to the failure mode, run your safety analysis, check the reports. And if you want to do some queries, you can do some queries. We'll see in the next slide. And even at the architecture levels, you can do some rule checks and see whether, example, you have some safety mapping which is already which is available for all the failure modes or not. So here, using the rule checks, you can, even before getting into the next steps, you can verify whether your FMEDA is clean or not. So this level, you can start with directly with the GUI. In a lot of these companies, they have, it's not like can't be done. A lot of these companies, they use this in XLS-based flow. They have some Python scripts for everything, and they run kind of thing. All these are integrated in a single GUI-based flow here, so making your life much, much easier. So this is what we do at the architecture level. We take the architectural FMEDA now, that's based on the estimated data. Sorry about it. We create the FMEDA, then we create a verification plan. Then we take this at the architecture level. Now we get into the design level stuff. We take the design, we are using the USF. We take the design, we map it with the verification or the implementation tools like Genus or the verification tools like Xcelium and Virtuoso for digital and analog simulations. Then we take this mapping. This data, what we collect, is called the overall chip design data. That we pass it on to the as an IC data back annotate with the architectural FMEDA. So this is the process where usually this is the cycle which happens in any of your safety cycles in any of the industries. Yeah, whatever we discussed in the previous slides, more at a GUI level. You start with the architectural FMEDA. that is the GUI which was missing in the two slides back. You have the architectural FMEDA getting created. Here you don't have any of the design data, but what you have is you only have the FMEDA hierarchy. You have the failure rates and distributions based on fully all the on like early estimations based on your rough analysis kind of thing. Okay, I know. Okay, these are the blocks which are there. This is the acid gates which I'm going to use. So roughly, okay, I'm just putting these are the numbers which might come here. So this will be a little bit optimistic side. So now I get into this, take the design, I implement the design, I get a netlist. From the netlist, I know what is the number of instances, what is the total area count, all these details, I just pick it. Tool is, the advantages, as we saw in the last slide, tool is directly connected with the genus, with the Xcelium and the Virtuoso platform. So tool can directly get this data. If you are using XLS-based flow, you need to manually again enter all these data by yourself. Whereas here, the tool is automatically connected. We know what is the instance or data which is there. It populates the data and automatically you see the, I think this is very minor, but you can see the SPFM data which is there. Compared to the previous data of SPFM, this is a little bit lower because now here we just put an estimated number, like more on the optimistic side. Whereas here with the design data, I have this, with the mapping, I have this estimated data a little bit on the pessimistic side or a little bit realistic. This, most of the companies, even without running your fault campaigns, they can stop here if it is going to be ASIL-B for most of the cases. For some cases, even with ASIL-B, you get into the simulation part. When you run the simulation data, now you have more accurate numbers what you have with respect to the design and as well as with the simulation data. This data is going to be more accurate, and here you have all these diagnostic or the fault metrics which are there, which will be populated once you have this verification data numbers again popped in automatically. You are not going to enter because again the MIDAS tool is directly connected with the simulators and directly it gets back annotated with this data. Once the numbers are populated, you can see the realistic numbers of SPFM, which is now 2% higher and probably now it is in the range of ASIL-B certification requirements. The same thing, what we saw in the GUI, can be also done using the USF commands. Very simple. Set FMEDA. I can set up my FMEDA. What type of ASIL metric is needed? Is it B or C or whatever it is? And what type? Is it an architectural or it's a detailed FMEDA? I can get that. What type of technology I'm using? What type of BFR calculation I'm using? I can set all these things using commands. I can create a technology for digital, and I can use that what is the fit data for it. And as I said, I can create, this is the parts and subparts, which I can create for my FMEDA. As I said, we can start with a CPU core. This is my CPU core. And for my FMEDA, I can either give, these are the instances of my part, or I can also directly give a gate count also for it. Both the things are possible here to get into the calculations. And now I can also add multiple subparts. One part or the CPU has multiple subparts. I'm here putting one subpart as fetch. I can have like multiple other things like add, subtract, multiply, or MAC, or whatever it is. For each of these things, I can again give what is the instances or the count data. Now for each of these architectures, I can create a failure mode, and also I can assign a safety mechanism to these things. So I create a failure mode and say like, okay, what is this type of failure mode which I'm creating, and what is the part number which is associated with this particular failure mode. I give this data and I can say like, what is the type of fault? Is it like a permanent fault or a transient, or what is it? I just can specify directly here. I can create a safety mechanism, then I can also apply the safety mechanism to this particular failure mode. And I can mention like what is the DC count for it. Like I can either it's a permanent or there is no trans, or there is a latency of 100%. All these data I can specify in command mode. Same thing you can do it in the GUI also. So for some people who are comfortable with the more command mode kind of thing, this can be there. And in the end, you can save this USF. Again, this can be for your one of your iteration of the chip or a part. And when you want to reuse it for a next one, you can load this USF. Assume now from ASIL-B you want to get into ASIL-C. You can use this, edit some of these numbers in this or in this, and get to the next stages. Again, a lot of queries can be done. You can again query what type of safety mechanism for a particular failure mode, or what is applied, multiple safety mechanisms or multiple failure modes. All these you can play with it. You can query whenever there is a USF is there. You can query it directly. It's like a Python thing. You can query it. And end of the day, once your safety campaign is done, you can generate a report once directly from this command, and you can generate this report either for a permanent, transient, or an overall report kind of thing, which you want to give it to your end customer. So that was the how at a very top level. Now we are getting into the details for the digital side of the verification thing. So as I mentioned, Cadence flows very seamlessly integrated with the regular logic verification flow. So if you see your left-hand side and the right-hand side, the flow looks more or less the same, right? So your functional verification or your safety verification, extra there is only two things. Here you have the verification plan. There you have the FMEDA, which we can call it as a safety plan. Here there is some verification manager, which takes care of the various logical simulations, be it your formal engine, your logical simulation, your Palladium for emulation or the prototyping. So here come to the safety verification. Your FMEDA is your input. You take it. Your MIDAS platform is the overall safety planner, which integrates with your Verisium manager. We have a safety campaign app, which is the same Verisium stuff. And this again interacts with any of these three underlying tools. So you can run directly the formal, the logical simulation, and the Palladium part. So primarily it is the logical simulator which will be there. So you used to compare the good simulation from this part to the false simulation in this, and you use the formal to prune the testability or the logical false analysis. The flow is very, very simple. That is the biggest advantage using this flow. And as I said, we start with one GUI at the top. So for the end user, it is going to be a top level MIDAS safety platform GUI from where he's going to launch things. And then whatever, if there is a DV engineer who is already using a Cadence flow using the Cadence Verisium manager, things are going to be the same for him. Like extra part is just that extra part for any safety engineer, he needs to understand the FMEDA concepts and things. Otherwise, rest of the flow is going to be as simple as that. When I say rest of the flow is same for logical simulation using XLib or as well as STL flow for the emulation kind of thing. So that is how we do things currently. However, as you guys note, one other point, the fault DB is common for all the three engines. That means the same fault DB which we are using for the regular logical simulation will be used by the formal engines to prune some of the fault stuff, and also the same engine can be used at the Palladium level. So if you're having an overall SOC level campaign where you are using some of the STL libraries to do the emulation as well as a regular SPUVM flow also to do some of the logical simulations, you can have one single fault DB where the entire campaign, entire DC coverages can be mapped to your overall test plan. We'll see that in the next slide. Yeah, I'll just build this. So this is what I was talking in the previous slide. So overall, for a user, as we saw in the previous slide, the top MIDAS platform is there. That will give the FMEDA as an input to the Verisium manager, safety app on that part. Now this has the various lists of your fault list, your strobe list, your test list, and your campaign configs. And this you will be running with any of the engines. We forgot to add the Palladium safety, but assume this excellent safety and Palladium safety can be done at this stage. And you have a common fault DB. So this common fault DB is used by the structural analysis or the formal engines for your overall fault reduction things. Why do we need fault list reduction? However efficient your logical simulator can be faster or whatever it is, this is a very expensive campaign, right? Like your fault campaign is going to be much, much expensive, where you're going to run n number of runs of this thing. So instead of that, use the structural analysis or your testability analysis to overall prune your fault list. You can collapse it. You can, if some of the accessors allow the structural fault sampling also. So you can just sample either 1% or 5% of the overall faults and just use them, or you can use the fault collapsing mechanism, which is inbuilt in the Jasper engine. Use that and reduce the number of lists which are only most necessity campaigns. You only run those campaigns, right? So your main goal is to keep the optimized list of the fault list and run this, so that once you have this campaign executed, you get the DC coverage or your metrics, fault metrics, you pass it to again to the Midas platform, which is again the big GUI. You get to the safety metric from the fault metrics. You get the DDD, all these campaigns, get it annotated with the Midas tool. Midas tool automatically calculates your safety metric. So this is there. And the advantage of using this tool, you can see this point. If people who are already using vManager might know, this is the vManager GUI, how it looks. So you can see for in a normal vManager logic simulation campaign, you get your coverage mapped to your test plan kind of things, right? With the safety campaign, what it does is all the DC coverage is getting mapped to your overall your fault list and other things. So the same look and feel, extra safety related stuff are getting added to the GUI kind of thing. That's the biggest advantage. So for a DV engineer, the amount of learning is very minimal. So you can just get into anyone who can get into the basics of FMED, and this thing can be easily trained or easily get into the safety verification flow. We'll get into some more details in the next slide, but high level, this is the overall fault campaign management, what we are doing. So most of the things are automated, and as I said, we're not just doing in simple automation of just getting this and doing this, but we are using the best of the engines which are there in the industry, like the formal engine or the Palladium engine, to get to the optimized list what we want in the best possible time also. Again, we support both the serial and concurrent engines. Usually for a big A, like more of a analog mixed signal designs or DMS kind of designs, people usually start with serial and stick with that because of the debug and other things there. But usually for a big D designs, like a huge bus, ACB or ACC, you want to run n number of campaigns, you can directly start with a concurrent engine and run things. And if some particular test is not working, or you need to debug, or you need to launch it, you can immediately switch to a serial mode, and you can, primarily for debugability purpose, you can run it. Something is not getting executed in concurrent, you can very well switch to that particular test, or this alone, campaign alone, you can move to a serial flow and run it, so that all you have the best of throughput and the best of debugability, both you have in the single thing. So we support all the three. You can start with serial, you can start with concurrent, or you have a hybrid flow where you can start with either one of this and switch to other things. So we have all the support for this. We also have a flow where we can, we call it the capture replay flow. We also have support for capturing and replay. We capture at some strobe list, we can capture the data and we can replay it. This is for huge designs, we can do it. We support it, but yeah, we need to exercise it with caution in cases we see it working. Our this can be a little bit error prone if you're not doing a capture properly and replaying it at proper cases. So, but we do that support also. So anything for higher performance or throughput, use the concurrent mode, but for debugability or for mixed signal designs, start with the serial mode. Same case with Palladium. As I mentioned, flow is literally same. You just replace Palladium with Xcelium, and you can see this is nothing but a simulator flow, right? The simulator flow just replace the engine. This engine is like a Palladium engine and IXM compile. There is again, you can see there is a central fault database which is there. You can run the good simulation, you can run the fault simulations, and the end you just do a compare and get the fault DB and pass it to this. Mostly, as I said, we are using it for the software stacks, or now there is a bit of the virtual platforms which are getting developed. Like we have Helium, there is a lot of these virtual prototyping platforms which are there, where the software teams need like a lot of software stacks to be created for this automotive, right? Like OEMs, they need a lot of these things. So for it, when you are moving to a platform like a Helium kind of thing, So there you can't run those software stacks with logical simulator. You need a hardware platform. So those things will be connected, your virtual platforms will be connected to Palladium. You run the entire software stacks through this and get your safety mechanism. What we saw in the 2 slides before on the Jasper, as I said, we do a structural analysis. First, we annotate the untestable faults in the database. So here we ignore all the safe faults and we check only the prime faults, and we will also, whatever the faults are, the equivalent faults of those prime faults, we kindly ignore it. As we know, like, for example, if there is an output which is prone to multiple inputs, if there is a stuck attack, one of these inputs is going to propagate to a lot of these inputs also. So I know I can just ignore all these equivalence faults and just check on only the primary fault kind of thing. Again, then once you do this, you use the FSP test constraints to check all the particular tests. You can see only what all is needed for it, and then you can all the pruning test-based faults can be dropped. So once it is dropped, you have an optimized fault list which will take to the Xcelium safety campaign, and will get to the you will get to the annotation. Once it is there, in the end you will have still some 10% of remaining fault list which is there. That till this we have all these things are part of the flow. You can still use Jasper, some of the properties of the FSP app which we have. Use this, and then you can interactively do some analysis on it. So on the remaining 10%, still it can do some analysis on the unobservable faults, and you can classify it into the various things, DD, DDU, or the UT kind of thing. So this, the green part is there with the tool. The Jasper thing is the additional thing which is needed in the part of the flow. But all these are, if you're writing a script or it is part of the campaign, in the campaign configurator, you can select all these things and just run it part of your one campaign kind of thing. This is now getting more and more needs for simulation IPs for automotive. As most of you guys know, Cadence is the market leader in the verification IPs, and specifically focusing on automotive, we have a lot of these VIPs which are like very much matured and capable. As I said, we are moving away from a traditional copper wire based mechanical networks to a lot of these bus based networks, where you have this Ethernet TSN based TI, MIPI, or even now we are seeing like this PCI protocols and other things getting into pictures, and we support all the CAN-FT protocols. I think now there is, again, I think going forward there will be UCAE and other things also which is coming in into the, because of the chiplet based design. So we have the support for even UCAE and probably CXLs and other things. This is what I was mentioning on the need for Palladium, because no longer it is just hardware only area which we are working, right? We need to not just the STLs we are working, but we also go beyond that, right, on the software stacks kind of thing. So all the OEMs need the entire software development. So can they do it before the hardware is ready, right? So what they need, that is where you come and get into the virtual platforms, or Cadence thing is called Helium. But you take a time loose model, you create a model which is a hybrid model which is available. It's loosely timed, but you can do a OS booting. You can get it like early, even before the hardware is completely ready, because you're just making like a model, virtual model. You can run it on any standard Windows OS kind of stuff. This will have more details because it is primarily for the software development, but you can still have a view of your memory registers, your overall control, like your interrupts and the pins, high level of abstraction that is there. Take this, now integrate that with your hardware, like Palladium or the Protean platform, which is already safety flows enabled on this. So you can run something which is already proven on your safety platforms. So this will give you performance, as well as this at a high level. Even before the final chip is available, you are also proving your software even before everything is available on the chip kind of thing. That's the advantage of getting into the virtual property. Again, this means okay, VIP, I can just use it at the logical simulation level. Then when I'm going into hardware, okay, do we have the hardware-related acceleratable VIPs. Yes, so all these are the acceleratable VIPs which are available for the automotive market. You have the MIPIs, the CANs, the Ethernet, the 5G related VIPs. All these are available for AVIPs also. That means, as I said, not just in logical simulation, you can do the entire setup and verify things in the hardware also, like your original emulation platform. Getting into safety, as I said, again, Cadence is one of the leaders in the simulation platforms. We have our Midas platform is integrated with the AMS campaign and the simulators. We directly collaborate with the Virtuoso platform and the Spectro. We have the reliability analysis Legato, which is there. So we take this, we run the campaign, again the same flow, we just map it to the Midas platform and get the back annotate the metrics direct to the Midas platform. So what we do, similar to your digital stuck at 0, stuck at 1, here we have the short, open kind of faults which are there. You identify the faults, you simulate it, similar to the good and the bad simulation, then you get the overall coverage analysis, which you can directly see it in your Virtuoso AD. So directly, like similar to what the vManager is directly connecting to the Xcelium and you're seeing things in vManager, you can directly see the analog coverage data in the Virtuoso. Summary, this is the overall advantages of Midas platform. You can have one single window, a comprehensive flow for both architecture and the detailed FMEDA. We support USF for interoperability. It is directly linked to digital and analog mixed signal flow. And it is also linking to the digital synthesis and the implementation tools. So overall, directly from a single platform, we have the best-in-class verification management solution, which is based on our vManager campaign. That is where we launch our fault campaign stuff. So it gives all the data for your overall functional verification and your fault simulation, as well as the debug experience is like far superior because you're seeing as it is. It's not like two different tools or anything. The same tools, the same debug experience what you're using for logic simulation, you can, or the AMS simulation, you can use it in this particular flow. And as I said, you can use the fault emulation flow using our Palladium safety to completely verify the entire SOC with even the software text like this. And all our tools are TCL1 qualified, any of the Cadence tools. However, for any of the safety specific flows, we are already like TCL2 certified. So from these versions onwards, all the new releases which are coming in are always constantly in the way towards the certification, and we are already there. We also do functional safety services. So someone is a new OEM or a semiconductor company was getting into they want the ISO26262 certification. We take the complete flow with them. We can starting from the architectural analysis till the safety manual creation. We work with them, get the things done for them. Some of these partners of Cadence who had used our flows and successfully the chips are already in some automotives like your TIs, your STs, your ARM, your Marvell, and the big guys. All these are some of the platforms where we have used Cadence tool successfully. That's the end of my talk. I think I'm on time. Okay. Any questions or anything? Yes.
Is there any one-time difference?
Based on the how big is your campaign? Based on that, yes, there will be but not on the simulation. I think if this is going to run for 1 hour, probably this will take like 1 hour 10 minutes or something. That is the thing. But the number of runs what you run, that is, if you are specifying the cone of observability points and other things, based on that it can reduce kind of thing. But yeah, it's similar to your logical simulation runtime. Anyone has tried safety emulation flow any of these days? Because I was talking, and any of your companies, from my side the question is, any of your companies are doing like virtual platforms or getting into the emulation flows and other things as of now? Or mostly all of you guys are in the simulation market or no? You're using simulator based stuff or no? Campaign? Okay, okay. So this is getting more traction now. So I just wanted to, we have seen with some of the top guys we have seen, but I just want to gauge in this thing. You know, a lot of asks is coming also on that side. So any requirements or any needs more than questions, any other things from, because some of the guys are already doing things. So I think flow is there. Yes, yes. This is there. In the Cadence support site, you have this array case there. Okay, I think any questions on the phone? Oh, for previous, okay, 12 o'clock, okay. Okay, okay, thank you. Nice meeting you guys. Thank you. Hope you got some good information from this. Let's try things on the safety side and give us your feedback. We are ready to implement it. Can I? Oh. Is it because it's going on? Still? Okay, please.
Thanks, Sundar, for the presentation. That concludes this session of DV Club. A special thanks to all the speakers and to all the audience members for attending. Please spread the word about DV Club amongst your network. This is a growing community, and we want to ensure that as many verification and design professionals as possible benefit from the experience of having industry experts like Sarvesh, Sundar, and Mike talk about some of the latest industry challenges. Disha has asked me to announce about the next session of the DV Club. So we'll have the next DV Club on October 15th, and the focus will be on verification of chiplet-based subsystems. Chiplet is all the rage these days, so make sure that when you receive the notification, you click to the subscribe button. We'll have it here at Cadence. We'll continue to collaborate with Cadence to organize these events. If there are any questions that you have subsequent to the presentations, feel free to reach out to Disha. She will consolidate and she'll work with our speakers to get your questions answered. We should have the permission to share the presentation materials offline. So you should receive notifications in your inbox maybe over the next couple of days or so. And the recording should also be available in case you want to revisit. Okay, thank you very much for your time. Have a good day. Thank you.
Thank you, everyone. I just want to, in terms of I just want to report to all this. Please.